at the Rust FFI module and trying to use that to bind to a C library. The FFI module allows you to work with non-Rust types, and in this case, I'm going to be using it to work with a C++ library. This C++ library is for creating and comparing locality-sensitive hashes. These hashes differ from other hashing techniques that you might be familiar with, which are intended to create a unique hash for a huge domain of inputs. The purpose of locality-sensitive hashes is to essentially hash similar inputs similarly, so that you can use differences in their hashes to tell how similar the inputs are. This would be useful, for example, if you are editing text and you want to be able to see what versions of text or what pieces of textual content are similar to each other without doing a full text search, and using something like Levenshtein distance or something like that. So the first thing we're going to do is create a project. So it's cargo new, and then we'll do FFI. Let's do LSH FFI. Let's go in there. Let's cargo run just to make sure everything's working. Hello world. All right. So the next thing we need to do is actually get a hold of the C++ library. I'm going to use makefiles again to manage this project, because there's going to be a lot of command line operations I'll have to do over and over again. Let's start by making a phony TLSH. Again, the phony target will actually force the operation to be done over and over again. You can also use it to alias longer names, which is what we're going to do with this later. So start with git clone github, or git at github.com, and then it's my fork of the trend micro project. If that fails, it probably means it's already been downloaded. Okay, I'm going to close this up so I have a little more space. All right, so let's run that. All right, and so if I try to run it again, you can see it says it's already downloaded. So we've got it downloaded, and then to build it, go into the project. And they have a script in the root that actually builds the project. So let's do that now. All right, let's take a look at it. And so we've got a bin folder, we've got our header files in there. We've got our source directory in here, some tests and some test utilities. Right, so let's take a look at the binaries. Let's run it. All right, so we've got this first one here will let you compare files with some options on top of it. Compare digest. In this case, the digests are the hash of the input values, so the hash digest. Looks like there's some additional options, but we just want to focus on these first two and check those out. So we need to get some text. I like to use Star Trek Ipsum. It's a little bit more interesting to look at and a little bit funnier, I think, than lorem ipsum, which is kind of bland. So let's get a couple of those files in there, or get a couple files in there. All right, let's get a couple paragraphs. No, it's fine. Okay, cool. and then we're just going to do two identical files to start. Star Trek 0 HTML. Then we're going to do the same for another file. Okay. All right, so let's take a look at what happens if we provide these files. Star Trek 0, Star Trek 1. All right, we can see the difference between these two files. Let's take a look at what the individual hashes look like. What if I just do this single file? Okay, yeah, I guess you need to use this F. It's kind of interesting that the optional parameters first, but whatever. Okay, so this is the hash value, and it would be identical if we looked at the other one. So let's actually start changing the text on this Star Trek 1 file. Let's just take out the last word here. Cool, and so we can see the distance is now 20. If we take out a full sentence, what does that do? 52, so it's a little bit further away. Let's add a little bit of a preamble. Nonsense TNG episode. Now, so you can see that as we start to differ more and more from the original text, the distance gets higher, and as we're closer to the original text, it gets lower. Right. Yeah, I'm not sure what the difference is here. It's probably some formatting thing. So it's important to, I guess, normalize your files. Oh, there's still the missing transporter at the bottom. Transporter. Okay, now these should be identical. Okay, cool. Great. So we've got a little look at what the library can do. So let's actually try to get this integrated into our Rust project. And so the way I'm going to do that is I'm going to use this utility called bindgen. And so bindgen is a Rust application that will generate binding files from C++ headers. If we take a look at, or C headers, but there are some limitations that we'll run into pretty quickly here. So TLSH, include. All right, so these are the header files for the C++ library, so we'll be taking bindings from these files. So let's take a look at what bindgen outputs for these header files. Let's take a look at TLSH util. Oh, LS. Well, all right. Yeah. So these are bindings for the given file. So this H distance is what we saw used when we did the difference between the two files. First, it would create the hash, and then it would send the hash to this H distance function. Yeah, so you can see the inputs and the outputs are mappings to different C types. We've got uchar, we've got cint, etc. But there's no, this to hex and from hex, those are not actually the hashing functions. I found out before. The hashing function is actually implemented, or it's defined the TLSH H header, but there is something preventing us from actually generating those. I believe it's because, it might be because of some of these pragmas here, but I'm not positive because it doesn't look like there's anything wrapping this. So I'm not sure why it doesn't catch this class here. However, when I try to do the IMPL file, we'll see that there's this error here, unknown type class, And essentially, it's because bindgen and I believe Rust can't handle C++ classes. So what we're going to have to do is actually create a wrapper for the methods that we want to get or that we want to use on this C++ class. But that's pretty easy. Essentially, you just wrap the calls in a function and return the value. So let's actually define that. So we've got TLSH, Rust compat H, let's shove that down there. Okay, so let's start with just the hash distance function, because we can just H distance. Okay, so we can just pull this down here. I'm going to rename this get distance, just to avoid conflict with this namespace here, or conflict in the namespace. Okay, and then to actually run the get hash function, that's actually defined here and here as well. So these two versions of this get hash function, one allows you to reuse some buffer, and I assume this is, I didn't use this version when I was working with it before, but I assume this is the output buffer, not what you might expect the input buffer. So let's start get hash. Let's just pull this down here. And then this is something that only applies to classes, so we'll take that out. And we'll rename it to get hash with an underscore to keep it consistent. And then, so we also need to have inputs too. So this is definitely very OO style, but the hash inputs are defined on either this update or final method. So we're just going to take the arguments for that, pull it down in there, and we're going to take that out. So those are not important for us. So we've got our definition, and now let's create the implementation. So I'm going to just copy this Rust compat file. And then I am just going to paste it here into our source directory. Oh, I should rename it. And I'm going to still use C++ because I'm a little bit more familiar with that. And it'll be faster for me just to create the bindings in C++ than try to implement it in C. Okay, so here we need to get the to do get distance, we need to get the hdistance function, which was in TLSH util. And then in here, you just return h distance. And then we're just going to pass in the parameters. So this length value here at the front, that is defining the length of the hash string itself. I don't think that's necessary to expose that to the outside because the hash strings will all be defined by the library. So I'm actually going to load that in myself and remove it from one of the arguments. So it's actually called TLSH string len, and it's defined in the TLSH header file. Okay, it's going to continue to complain, but that's, there's not much we can do about that. Okay, so now let's do this get hash function. And this length here, unlike the one up top, is defining something that can change. It is the actual input data, and so we do need to actually get the length of the string here. It's not ideal to be working with pointers and string lengths directly. It can definitely lead to underflow and overflow issues, which are cause of a lot of different memory-related security vulnerabilities. And so it'd be better to be avoided, but I'm not expert enough in this library, or I'm not familiar enough with this library to actually recommend a patch to it. So I am just gonna sort of try to make the best of it for now. Okay, so the first thing I need to do is I need to make an instance of the TLSH class, and then I set the content. So this is data, and this should be length. All right. And then next, I'm just going to return the results of t.getHash. Now we will run into some issues with this implementation, but we'll approach those one at a time. So let's go over here and build our project. Make. Okay, it's building. Oh, I had forgotten to add this to our CMake file, so you'll notice that our Rust compat didn't get built. So let's go into the CMake file, and it's this one here and source. Okay. So let's just add it into this sources list. TLSH Rust compat. Okay, so it should either build or fail. Yep, there it is. And all right, cool. So the next thing to do is to see if it was actually built into the library. So I'm going to use the nm tool, which is a command line tool that lets you interrogate different binary files. For this case, we're just going to be looking at the symbols table for the given binary. So let's take a look at the lib. Let's pipe it through more. Okay, so yeah, we can see TLSH CPP, printf. Okay. Oh, here's our Rust compat. And what do we got? Oh, okay, we've got, oh no, sorry, this is IMPL. Here's our Rust compat. Okay, so we've got our getHash and getDistance functions, and it looks like hDistance came in too because we're including it. But you'll notice that there's this prefix and suffix on both the getHash and getDistance functions, and that's going to be a problem for us because our library won't know where it's been mangled to. So what we're actually going to use is this keyword extern C, and then we're going to wrap our implementation in that block. And so now this should prevent these from getting mangled. All right, so let's do make. Okay, and then if we look at nm again, all right, here's our Rust compat, and we can see that getDistance and getHash are not mangled, so we should be able to link against these in our Rust program. All right, so we've got the library producing the objects that we want it to. So now let's actually link those into the Rust project. So I'm going to go up a level. Then I'm actually going to create bindings. So let's do that. So we're going to put them in source TLSH Rust compat Rust, That's going to depend on TLSH, include TL, and then it's just this again with H. So we do bind gen, and then we're going to output it to this file. So this is a implicit variable in make. So if you use $@ I believe that it is this task, and if that's not the case, we'll just adjust it. I'm going to alias this so it's easier to remember. So phony gen bindings, and then gen bindings is going to depend on this. So I should just be able to run make gen bindings. All right, there we are. Let's take a look at those bindings. All right, there we have the definitions for our get distance and our get hash. It looks like we left the length in the header file, so I'm actually going to get rid of that. So we've got rust compat h. Okay, let's get rid of that. Let's run it again. All right, there we go. Compatibility is up to date, or sorry, our bindings are up to date, and we should be able to start using this in our implementation. Okay, so here we're just printing out hello world, but we actually want to start by printing out a hash. So let's create a function that calls our bindings. So input string, and that is going to return a string. Okay, let's just, I like to take things super slowly, so I'm just going to return the input for now, just to get the function compiling. And then we'll just print out hash 0, and then that's going to be get hash. And then for input string, I'm just going to use a bit of the Star Trek text. Let's just use that. That's plenty of text. Okay. Oh, into. Okay. Okay. So now when we run this, we should just see that string output. Yep, there it is. Okay, so let's get to work on actually using our bindings. So we have mod, then TLSH rust compat. Okay, so our function is TLSH rust compat, and then we do get hash. Let's just clean this up a little bit so it's a little bit easier to work with. Okay, so we need the data. So we've got the data, but we need to convert it into something that will work with this C type, and then we need the length. The length should be easy enough. So let's just do input length. And this is expecting a I32. So let's just do this as I32. This length is U size, so it is possible that it would be larger than what an I32 can handle, but that's just something we're going to have to deal with, unfortunately. So there could be an overflow here. The length should probably be a U size in the C library as well, since you don't really have the possibility of having a negative string length. Okay, so this is still having trouble, and I'll show you what it looks like if you just try to throw the string in there. Input. Okay. Just expecting this const u, and so to get this type, we actually need to work with part of the FFI module, which provides compatibility with C strings. So let's actually import those. So we're going to use std, FFI, and then we're doing CSTR and C string. Okay. So we need to get input C string, C string, new. That's from input. All right, and this is a result, right? So we actually need to expect unable to create C string from input. And you can just unwrap this, but I find it helpful to always have a message even before I have error handling. Because even though it's still gonna panic, it'll give me a message and tell me what's going on. I mean, if this was like for professional work, I would change this to a result and then handle the result higher up, or like handle errors in a consolidated place instead of handling them sort of ad hoc. So this should be input. Actually, this is looking for a pointer, so we need like input pointer, include or input C string into raw. This gives us a raw pointer. And so whenever you're getting a raw pointer in Rust, you should alarm bell should be going off because you are in the memory danger zone. All right. Oh, we got to cast it as star const u8. Okay. What's this angry about? Oh, sorry. U32. Okay, so that should be fine. Okay, right. This was U32, not I32. I'm not sure what the difference is in U size and U32, but they do overlap enough for us to handle reasonably sized text. But this call is now unsafe, so what we have to do is wrap it in an unsafe block. And that should let you know that anything that happens inside of there is a potential memory issue, right? So what we're doing is we're providing this U32, but we're also setting this pointer in. So we're going to want to be extra careful to make sure that we're handling the memory on this pointer correctly. But we'll come back to that when we look at using Valgrind. Okay. Okay, so this is saying it was borrowed previously, so that was up here. So we need to add clone to that. All right, and there we go. Okay, so that's going to be our output. Okay, and so the value we have here is, let's take away that semicolon, and then this is const star I8. So that's, so this is a little bit of an annoying part of this library, is that the different string types or the different character pointers are signed or unsigned. So let's actually take a look at that. Right, so you'll see here that the input for this get hash function is an unsigned char, but the output is a signed char. I don't know how necessary that is, or if it's just that, I mean, you can see that this it's quite a large type definition. I mean, not relative to other C++ type definitions, but possible that this was just omitted. So we're actually going to need to use a different part of the FFI module, and that's C-stir. So let's actually do that. Let's C-stir output equals C-stir from pointer tr. That's going to be our output. Okay. All right. And it looks like this is an unsafe call as well. So let's wrap that. And then we need to actually, so this is now a C-stir, so we actually need to convert this into a string. So C-stir output to string, no, to str. And then this is a result, so expect unable to convert hash to C-stir. And then we're going to turn that into a string. All right, so all of our types matched up. And let's try to run it. All right, so we've got some issues here. Our getHash function is not defined. And that's because we didn't actually link to the library. We just created the bindings and are including the bindings, but they're not binding to anything. So let's actually link to the project. So again, I'm going to do a phony task here, and I'm just going to call it run. So run is going to do cargo run. But we're going to add some environment variables that will bind the library. So we're going to update the Rust flags. Okay. And that's going to be in our working directory. And we're looking in the lib folder. Okay. And we also need to tell the bindings to look in that library as well. Okay, so the way we're going to do that is link it here. Link name, TLSH, extern C. Okay. And so adding them to the same block just applies this link to both of them. I just didn't want to repeat myself. This will be a little annoying if we regenerate the bindings for any reason, but it should be pretty easy just to recopy this and resave it. Okay, so let's try and make run. Okay, so we've got a different error here. Got symbol relocation cannot be used in making a pi object. So our TLSH library actually needs to use this flag in order to be compatible. So we're gonna head back to the CMake file and add that compiler option to the C++ and C flags. So to do that, we just set the environment variable flags, and then we're just appending. So we will include the existing values, and then do it is, where is it? Here it is. So we're going to include that flag. And then we're going to do the same for C flags. So let's go down into TLSH. Make it again. So now that we've recompiled with this FPIC flag, let's try building and running our Rust project. Okay, could not compile. Undefined reference operator new. So this is because the Rust project doesn't by default link to the C++ standard library, and that includes things like implementations of the new operator, delete operator, etc. So we're actually going to have to bind to that as well. Unfortunately, we can't just use the same flag we're using here, or we can't use the same environment variable we're using here, because the library is different depending on what platform you're using. For example, on Linux it's std, C++, and on OS X it's C++. So let's actually, what we have to do is create a build file. So we're going to go in here to our cargo file and set build to build.rs. And then we're going to edit that file. So build.rs. And then here, it's just a simple main function that prints out the options you want to add. So in our case, what we want to do is get the environment and print out the correct linker options depending on which environment we're building for. So let's let target, and then we're getting the target out of the environment variables. And this is the result, so we expect okay. And then if the target contains apple, we're going to print, so it's cargo rust c link lib, and then it's dylib C++. And then for Linux, it's the same, just slightly different. So Linux here, and then it's std C++ here. Okay, so we've got that linking in. Now we should be able to rebuild and run. Alright, so we've made a little bit of progress. Our hash value is coming back 0, so that's a little bit strange. I have to debug that. But it is building and it is running. But let's confirm that it's actually calling through. So I am going to output the pointer for this here. Let's take a look. Print line. So this is going to be the received hash pointer. And I'm printing out the debug information. Script. Alright. Everything's fine there. And then we go to rust compat C++. I'm going to use IOStream because I know how to use it for what I'm about to do a little bit simpler. I don't really have an opinion, IOStream versus printline. I found IOStream to be useful. Let's see. So I'm actually going to do auto hash here. And this should be, yeah, our const char star. And then I'm going to output both the hash's value. And the hash's address. And then we're going to return hash. So we need to rebuild our C++ project. And then we need to rebuild here. Let's actually make this a little bit more consistent. Received hash, and I'm calling it 8 address, so. Alright. Make run. Okay, so we can see our problem here. These addresses don't match up. And the reason for that is that this hash and also the results of this are values that are local to either this function or they're members of this TLSH object. And so when this function goes out of scope, those will be released from the stack. So what we're going to have to do is actually copy those into a memory location that's not going to get deallocated once this function returns. So to do that, we're going to create a new string buffer, static char hash, and it's going to be the size and then we're going to use stir copy and just copy it in there. So we also need to get stir copy from the strings library. Okay, stir copy's there. This variable is not shown. Oh, it has 6. Okay, that's funny. It says it's not defined, and then it says click to show 6 definitions. It must be just confused because the definition changes depending on which compile time arguments are given. Okay, so let's recompile this. All right, so we've got our hash coming through. That's pretty cool. You can see that the addresses match now and the values match. Okay, so what did the static do? So static, in the case of local variables, says that this address is going to survive until the end of the program. And that might sound like a memory leak here, but we'll see later that it's not, because we're actually taking over ownership of it here, and the memory associated with that address is now going to be controlled by this C string. So when this C string goes out of scope, Rust will deallocate it, or like however it's being used, like if it's consumed by this toString method, or if it just exits from the function, it'll be deallocated as expected. Okay, so we've got that working. All right, so we've got the outputs matching. We've got the hashes or the addresses matching. So this function is working as expected, but we should also do a little bit extra work because we're running these unsafe blocks. So that should give us some idea that we might need to do a little bit more work for memory handling. So I'm actually going to run this with Valgrind. And if you haven't used Valgrind before, it's a pretty useful application for finding memory leaks. So I actually need to split this out. So cargo build. We're just going to use the debug version of the library. So let's target debug this guy. Okay. All right, so run is going to depend on that binary. That binary is going to be built using that. And then I am just going to run valgrind that library. And so now when I do make run, it runs with valgrind. Okay. Yeah, so you can see that we've definitely lost some bytes here. So there's definitely a leak. So let's add this leak check full option. And then run it again. Okay, so this is great. It kind of gives us like a stack trace for our memory leak, and it looks like they're all from the same frame. So that's makes things a little bit helpful. All right, so we've got string here, line 11. Here we go, line 11. Right, so it's when this C string takes over the pointer, and then somewhere along the way it gets lost. And because we're wrapping here in unsafe, we should think that it might be in here. And so we're sending this input pointer, and it's being moved or it's being borrowed by this get hash function. But get hash is implemented in C. It doesn't know that it's expected to release the memory or to deallocate the memory. So we actually need to tell Rust to take care of it. I mean, it's possible that you could use the free function in C, but the Rust documentation explicitly says you should not do that. And that kind of makes sense because you're using a C library that, well, one, you might not be able to adjust, you might not be able to change the source for, but you're also changing the semantics of the C library. Like perhaps there was some reason not to free the memory up there, or the C library assumes that the caller is responsible for it. So we're actually going to have to reclaim the memory here so that it gets deallocated as expected. Okay. So to do that, we're going to have an unused variable, and then it's another unsafe call C string from raw, and that's going to be our input pointer. So we're taking back the memory after the C call. So now when we run valgrind, I didn't rebuild, I didn't do that. I'm just gonna do that every time and then take that out. Yeah, sometimes the dependencies for make can be a little tricky. So I'm just going to move forward, not worry about it. All right. All heap blocks were freed. No leaks are possible. Cool. So we've reclaimed it here. And as I mentioned before, even though we're taking this static string in from the output, because we're loading it into the C string here, the Rust runtime knows that it has to take care of the memory involved here. The only place where we had to do anything additional was when we moved a pointer into the C library. So pretty cool. So with a combination of Rust and valgrind, it was pretty easy to find all the places where the memory was and was not taken care of properly. But yeah, thanks for watching. I hope you enjoyed my demonstration of like how you can integrate a C++ library into your Rust program. I think I am going to follow through and try to create a crate from this C library that's going to take quite a bit more work and back and forth with people that have more experience creating crates and the actual C library maintainer. And I don't want this video to be, several weeks long, so I am gonna do that afterwards. All right, thanks for watching, and I hope you enjoyed the video. Bye.